Before we start, I just wanted to remind you that myself and my team, we have opened a parametric design market, and where we're actually placing up some of our scripts and design with us and help us to make more videos more often and so on. Please consider approaching something from there. Also, my colleagues and myself were giving online classes, both individual and group. So you can also apply for those courses by sending us a direct message on our Instagram or to our website. The links are going to be in the description. So having said that, let's actually start with the second half of our exercise. I'm just going to remind you where we stopped at last time. So as you can see here, this is our parametric grid made with these are the panels made with the help of this script. You can find it in the first part of this tutorial. So as you can see, these panels, they get opened together, and they are located on a flat surface, right? So today we will be making these panels on a curved surface, which is the surface of this tower, right? And we'll also make sure that each of these panels will be opening independently of the other. So they basically don't have all the different opening ratio, let's say, right? So let's move on. Switch to the shaded mode, right? So it's not, so it doesn't distract us, this image. And first of all, I'm going to also move this part of the script forward because actually we wanted to start with doing some optimization and adding some, first of all, we need to build a base shape, and then we need to optimize it to make sure that the panels are represented by equilateral triangles. So let's start. As usual, we start from constructing a point, right? So we say construct point. We build the range instead of series, right? So let's say our tower is going to be 100 and maybe 60 meters, I think. 60. We connect 60 to the domain because this is the height, the total height of the building, right? And for the number of points, I'm going to say 12. Probably should be enough. Also, actually, what I'm going to do, I'm going to say we're going to use the Grasshopper to control the tower curvature because it's not really a cylinder, right? It has slight curvature, so actually this should be connected later on. We have 12 steps. We connect to the Grasshopper, and then we say, actually, I'm sorry. The Grasshopper for the radiuses, right, of the actually tower floors. But for the height, we're going to use this. So we take the same range. We add 60 here. We connect it to Z, right? So we create the sufficient amount of points. Then we take the circle component, this one circle in a plane, and we use this Grasshopper to generate the radiuses. So let's say we map numbers, right? We say bounds. So let's say bounds, right? So construct domain. Right, so and then then the radius is gonna be from I'm gonna make it dependent on the height. So I'm gonna use multiplication and use a certain factor to generate the smallest and largest radiuses. Right, so let's say it's gonna be 0.15 maybe, something like this. Let's see if it's gonna get really that big or it's gonna be enough. So let's make it like this. Here we can have our slider. For now, I'm going to keep them the same. And let's see how it's affected. Yeah, this looks okay to me. Maybe even make it even a bit bigger. Let's say 20. And the maximum one will be 24, probably. And then the radius of the graph will be used to change the curvature. So I'm going to make it symmetric like this. Right? So the building looks a little bit like wine pipe or something like this, right? So it has a bit bigger radius somewhere in the middle. So now I'm going to make it more or less symmetric as much as I can. I'm also going to switch off the grid so it doesn't doesn't distract us, and then I'm going to make a loft from these profiles, right? This. So here comes the tricky part, actually, because we need to take the panelization, right? We need to do the panelization. But if we carefully look at this tower, right, we should not cover the entire facade. We cover like half of it. So in order to make sure that we cover a part of this facade, let's use the isotrim, or we can also use parametric stabilized surface, but let's use isotrim. We have this one. So we take the surface as the domain, sorry, as the surface, and then we also need to reparameterize it, and then we need to take the domain. So we go to maths, domain, construct domain square, like this one. And one of them should be from 0 to 1, right, like it's set by default. And the other one, we need to merge and make it from 0 to something like, I don't know, 0.30 maybe, something around this number, like that. Well, okay, so what is... yeah, of course. Sorry, I confused this component with parameter stabilized, but yeah, the domain should be from 0 to 0.30. And now, there it is, right? So, if we don't like the location of the surface, if we want it to be somewhere here or here, we can rotate not the surface itself, but we can rotate the seam on this curve, right? So we take these curves. Here we need to say right click and we say reparameterize. And we take something like 30 maybe also, right? So this way our surface, you see, will be, so we can control the position of our facade. Let's keep it somewhere here. Also, actually, I might make this division a bit smaller. Let's say 0.20, maybe 21. And then I'm also going to increase a bit this rotation. And maybe we can also make this entire thing a bit. Yeah, I think we should do it. Yeah, we should be fine. We can also change a bit the curvature. We can make it a bit smaller. Right? So our goal is basically to make sure the surface is not too doesn't have a too crazy curvature, right? So it has a bit more moderate curvature. Okay, great. Now what we need to do, we need to go for the Lunchbox plugin, right? This one. We take the triangle panel B. It's important because because there are multiple ways of triangulating the surface, and this is the way that we need, right? So it should look somehow like that. We need to make sure that these triangles are as close as possible to being equilateral, although we cannot make them completely equilateral because the surface does not consist of completely equilateral triangles first, and second, it has it's double curved, right? So it cannot be completely triangulated by completely equal triangles, right? And also you can see that we need to create these sliders, and we need to make sure these triangles look more or less equilateral. So basically we can take view at edges. We can check, we can see length, and then we need to have a look at how similar it is, right? So you see that the larger one is the actual side we are looking for. So it's almost the same. Maybe we can make this thing a bit more pronounced, right? So make this thing a bit more equilateral. Maybe this is not as equilateral as we want. I think this ratio gives us an okay result. So let's keep it like that. Because we're still gonna fix that at later stages using Kangaroo, right? So Kangaroo plugin anyway, right? So yeah, so this is fine. Now what we need to do, we need to get rid of those triangles which are the smaller ones, right? The ones on the sides. Yeah. So how we're gonna do it? We're gonna take the area, right? And we know that these triangles, they are significantly smaller than these ones, like twice as big as these ones are twice as big as the smaller one, right? So we need to get the bounds. So we get the smallest and the biggest areas, and we can say deconstruct domain, and we're gonna take out all the triangles which are smaller than the half of this domain. So we're gonna say subtraction, and we're gonna take the largest surface and subtract the smallest surface from largest area and subtract the smallest area from there, and then we get this difference basically, right? And then we say yeah, we can actually we need to find the middle, and the middle will be, yeah, the middle is going to be this thing divided by 2 plus the smallest plus lower limit, right? So we get this number, we add the start here, and this is the area we're getting, right? Like half of the middle of the domain. And then we say if the area is smaller than this number, if it's larger than, then we keep it. If not, we get rid of it, right? So, and then we compare the overall areas, like all the areas with this one. This, say call pattern, right? So like this, and this. So there we go. These are our triangles, right? Which we're gonna take forward. So we take the view of edges. Right, there we go. So I'm gonna hide everything from before, and now it's time for us. Actually, I'm also gonna move this thing a bit forward, so it doesn't bother us. Yeah, so we need to do now we need to make sure all these edges are gonna have the same length. Now we actually have to make our triangles equilateral. So the way we're gonna do it, we're gonna go to the Kangaroo plugin, we're gonna take the main component, the bouncy solver, right? We say merge, and we basically just need to provide two Kangaroo components. First of them is show, so that the first item, first thing from here will be these curves. Second one will be the modifier, the linear goal, saying equal length, right? Because we want, what does it mean? What does it mean equilateral triangle? Equilateral triangle is a triangle which has all the sides equal, right? So we need to make sure that all of these triangles have the same sides, basically. And then we connect it to goal objects, right? And also we say the button, we use it to reset the solver. We also take the Boolean toggle, which will help us to start or end like stop the solver or let it go. And then we take the line component, right, like line container. And after that, we also need to say clean tree, so we can because you see we have some nulls. Nulls are basically the modifiers which are not lines. That's why when we connect them to the line container, they give us a null. And yeah, so you see we have 594 of these lines, and then we need to say the length, and we need to check. We need also to say create set. Create set. So we can check if all the lengths are equally long. Well, seems so, right? Some of them are actually some of them are a bit longer, which is not good, but it's okay. And we'll handle this. So what we need to do, we also need to restart this. You see, it deforms the overall shape a little bit, but as a result, we're getting all these parameters in place, right? So we are kind of that's our goal, right? Our goal is to get these lengths same, and yeah, you can see it kind of works here, right? So yeah, so we have all these lengths equal. I mean, almost equal, but this should be enough. This is like we have 6 digits after the comma, so it should be okay. Now we also need to turn them into closed triangles, right? So let's disable the solver because the result is already saved here. So it's fine. What we need to do, we need to make sure these curves form closed triangles, right? And now we need to say partition list, right? So like this, we say 3 because we need to make sure that 3 lines are back in one branch, and then we say join curves. So now if we have, we have our data in order, right? Because we have this thing or structured here, right? So we have 198 branches. So if everything is correct, we should have 198 closed curves, which we have, right? So great, this is fine. And now before we connect this to our setup, here I would like to do one more thing, because if you remember the previous exercise that we did, we used this surface to generate the normals, right? To make sure that these points will be moving, they will be moving perpendicularly to this surface. So we actually don't need this surface. We need these curves and normals to these curves. So we need to say planar to get the plane of these curves, right? We say deconstruct plane, this one, and we are interested in this z vector, right? So instead of this normal vector, we have to use that z vector. So we come here, and then we don't need this setup anymore. We don't even need this surface anymore. So this should be fine. Why do we do this? Well, because if we look at these curves, right, the optimized ones, and the surface here, this one, we can see that these triangles, they are not always, like their centers, they are not always, let's say the normal to each of these triangles is not always the normal to the surface in a corresponding location, right? So we can use this surface as a base if we are dealing with a cylinder, with a perfect cylinder, right? But if it's not a perfect cylinder, which is not, right, we will get some distortion. So it's better to use the curves instead of the surface. Let's have a test. Let's see how accurate is this setup. So let's say, I think it should be okay. We just need to get rid of the last 0 in this setup. So let's say 2 and 3, right, like this. And we connect it here, and let's see how we'll go. You see, it works. The only thing here is that all these triangles, they are pointing inwards, which is not good. So the only thing we have to do, get rid of this relay, and then we also need to reverse this vector, right? So we need to say negative. Very good. Okay, you see this thing works now, right? So this is the setup that we have here, which is exactly what we need. And once again, this geometry is not changing and it's not folding because of deformation or because of scaling down. It's folding because of these, let's say, panels. They actually rotate, right? So you see that when we open it, gets opened and the facade gets flatter. But once and also this point moves as close as possible to this vertex. But when we start folding these panels, you see these points are moving and these panels are rotating. And all in all, this facade opens up. Basically, the facade, each of these, let's say, three-sided stars, they fold like an umbrella, right? But the facade itself opens, letting the sun go in, right, into the building. And you can see it in the shade, right, how it changes. So you see now, this it gets very dark, very solid, so it kind of shades the building, and like this it gets open. And now the last part of our exercise today is actually making sure that each of these triangles will be opening, each of these, triangles, let's say, triangular sectors, it will open independently. So it will have its own amount of openness. So the way we're going to do it is also pretty simple. Let's take these polygon centers. Let's take the full point, and we're going to be using an attractor geometry, right? So let's actually create. Let's actually take the base. Let's take the base point as a center for our. Let's imagine our sun orbit, right? This. So okay, this point. Let's say we take the circle, the large one, and we also need to take the x. Let's actually say vector x, y, z. Let's say it's going to be 45, 45, 45. I will show you why in a minute. And then we say plane normal. So we use this. This is going to be our z-axis, and this is going to be our center, right? So this is our plane. And we can also make. Oh no, let's keep it like this. And then we can also rotate it in base x1 plane. And so this, let's say 30, 22 degrees, something like this, right? Maybe something like that. If we can put it as a negative. Okay, perfect. Let's say 60 degrees. All right, and then we say circle, right? And we make the circle something like 240, more or less, right? Well, it doesn't too much. Let's make it smaller. No, smaller. I'm not particularly happy with this thing, so let's actually I'm quite happy with this. Let's make it a bit bigger. Yeah, so something like this, right? And I just want to make sure that this thing is actually going to be different, so that one side of this facade is going to be different than the other. And so say 45 degrees. And then let's create our sun. Let's say evaluate curve. Right, so let's say this. We have to reparameterize this curve. We have to create a slider from 0 to 1 with 3 digits after the comma. this. Alright, so take it like this. Actually, I should flip this. And it will be more or less similar to an actual curve. Also, by the way, considering that this circle is not going to move completely, I want to split this curve into two. It doesn't really matter, as you can do it later. So let's start from here, right? In the front 0.5. And then what I want to do, I want to use not the distance, because the distance from this point to this point will be kind of the same. I want to use the vector from between this point and the center point of these triangles. And I wanted to compare with this vector, right? So let's take the center point from here, right? Let's say vector between 2 points. This point is going to be A, and this point is going to be B, right? And we're going to say angle. We're going to say angle, right? Angle between this vector and the perpendicular to these triangles. So let's do vector display. So we take this vector, we take this anchor point. So you see, basically these are all vectors. Actually, maybe it's better if we take it from the point to the sun. Right, so like this. So you see these are is it? Right, because we need to take so these are the vectors, right? And the other vector is going to have the same point, but a different vector, the z vector, right? So these are this is one set of vectors, and these are the other set of vectors. And we're going to be measuring the angle between them, right? So these are basically the things we're going to measure. So let's say now remap. So we can use first of all degrees, right? Then we say normalizer. It's a component from from Heteroptera plugin, which is a really nice one. Least normalizer, right? A really nice plugin. We recommend you to download it. Take the graph mapper. Basically, what it does, it just changes all the values into the domain from 0 to 1. So to speak, it reparameterizes the values. And after this, we take the bounds. The bounds need to be flattened because we want these bounds to apply to the entire data tree, right? And then we say construct domain. And you remember last time we used this as we started with at 0.15 and ended at 0.95. So let's type these numbers so that the actually no, it should be the opposite. The closer these vectors are to each other, the more right, should be like this. Because the closer these vectors are to each other, the more closed this triangle has to become, and the farther they are, the more open it can be. And let's connect these numbers to, let's type this first of all. Let's connect these vectors here. So you see here we have 594 parameters divided into 198 branches. Here we have 198 branches. So there we go. You see? Basically, these panels, they are very similar. They're basically almost perpendicular to the sun rays, let's say, right? And that's why this is the part where the facade gets really closed, right? But here, for example, there are almost no direct rays. It touches these panels, but it's not really perpendicular to them. That's why they are very open. If we want to highlight this contrast between these different panels, we can go for graph types, and we can make it as a Bezier, and we can change it to something like this. So the contrast becomes more obvious, right? So we can see where the facade actually changes. So let's give it a try. Let's give it a try by moving this point. I'm actually gonna edit the slider and set it from 0.5 to 1. Right, so let's say we change this to something like 0.65 just to see that how the trajectory, yeah, see, basically moving along, and you see that the sun is somewhere here right now. So if, yeah, also if you want to go really crazy, we can also, I mean, not really crazy, but if you want to make sure that we can visualize our sun and the trajectory, sun path, we can also make something like this. Make a really large sphere. We can also use custom preview to show it. I'm going to use some yellow or orange color just to support this narrative of yeah, something like this, right? This thing. And yeah, of course, we can also highlight this trajectory. So you see, maybe we can also make it a bit smaller, just so that the facade looks a bit bigger in our viewport. But you see that basically here, our facade changes depending on the movement of the sun. So let's hide these things, let's hide these things, let's show them. And yeah, I mean, if we want to really animate this sequence, we totally can do it. It's just that we have to, yeah, we will have to be quite careful about that. Also, we cannot probably move it in real time. I mean, we can, but these operations are a bit heavy because we have quite a lot of these panels. So I'm not sure if we can really see this result very well in real time, but we can try. We can try. Also, I'm gonna rotate this thing a bit more. Let's say somehow like this. Maybe we can even make it 30, but in the other direction. Yes, something like this. I think maybe 45 in the other direction might work quite well. I mean, we can adjust it, right? So, but my main point is that you see that how this tower, how this facade changes depending on the trajectory and orientation of the sun. Let's give it one last try. Starts here, starts moving. Yes, to this position, right? And gets to this position. You see how it changes, right? So the main change happens in this domain more or less, right? So you see, so this panel was open and this one stayed the sunlight. We can also last thing we're gonna do. We can also take the facade of this thing, right? The entire loft, overall loft. Actually, yeah, we need to make an offset. So let's say offset circles. Let's offset it by 2.5 meters to start with. So that's smaller. Here. Yeah, you see. So basically, here you see the shading ability of this panel. We can make it a bit, the offset a bit smaller. So it's, yeah, there we go. 1 meter is sufficient, right? So you see how this changes the shading of the facade. So this relatively small script is basically everything you need to make this Al-Bahar tower facade in the right way. So if we're talking about the real facade, it was way more complex than this, but the logics, the geometry, and the Grasshopper definition, first of all, the geometry of these panels is correct here. Great. So, yeah, thanks a lot to everyone who watched this video to the end. Please leave your comments. Let us know what you'd like me or my colleagues to talk about next time. Maybe there is a particular building or a particular topic that you'd like us to cover. Support us on our parametric design market. DM us if you would like to get a course. And yeah, staying in touch. Goodbye.